Good morning, all of you. My screen is visible. Anybody? Anybody can respond. My screen is visible. Hello.
Yes, sir.
Okay. See, today we'll see the three-phase control rectifiers. When compared to single-phase, three-phase control rectifiers will be used for high power rating the load applications. Normally, we have noticed the single-phase control rectifier. All control rectifiers will repeat here. Only the input side will change. Input is a three-phase supply. Now we'll see the some comparisons, advantages, all these things. Generally, this will be used for large power applications. That is a three-phase AC to DC converter. So that will be common normally. Three-phase to AC to DC converter is a common one. Another one is various types of rectifiers are there. So that is you can see half wave rectifier and then semi converter and then full converter and dual converter. So the difference between these three things are as you noticed in the single phase control rectifier, half wave rectifier and then full wave rectifiers are there. Here also we can notice the thing is half wave rectifier is a 3 pulse converter and then semi converter also 3 pulse converter and 3 phase full converter is a 6 pulse converter. And another one you can see here 3 phase dual converter. This will be as a two fully controlled converters connected in anti-parallel. Based on quadrant operation, we can say that there is a 4 quadrant operation. So earlier we can observe that in the case of or you can say that single phase converters and then 3 phase converters, both things, whether it is a first quadrant or a second quadrant or fourth quadrant, anything. These are all the normally if we consider as a single phase fully controlled rectifier will give two quadrant, that is a first quadrant, another one is a fourth quadrant. But if you connect another fully controlled converter in anti-parallel, you will get it as a all four quadrant operation. So second as well as the third. So this is the advantage once if you use as a full two fully controlled converters connected in anti-parallel. This either may be in the single phase case or maybe three phase. Both controllers will work dual converter. If you use two single phase fully controlled converter connected in anti-parallel, that is a single phase dual converter. Or if you use three phase full controller and connected in anti-parallel, that we can make it as a three phase dual converter. Now half wave converter is rarely used in industry application because that is only the 3 pulse converter, lot of harmonic will be there and that's the reason generally we don't prefer that. And semi converter and full converters is commonly used in the industry application. Dual converter also when the reversible drive application, because as I mentioned in a dual converter you can see that all four quadrant operation is possible. This is a forward motoring operation and then reverse braking operation. So like that forward braking operation, then reverse braking operation. So all these things you can possible by make use of a dual converter. So that is the advantage by using as a dual converter. So that is the reason whenever you require all four quadrant operation, we can go for as a dual converter. That too high rating application, several megawatts also we can use that. So then we will start with three phase control rectifiers advantages over single phase converters. As you mentioned in the case of earlier, single phase converters, we notice that. Now what we want to see is advantages of a three phase converters over single phase converters. Now first one is provides higher average output voltage. So in case of single phase, you can see that, whereas in the single phase average output voltage VDC, that is nothing but a 2 Vm by pi into cos alpha. So that is the single phase average output voltage. Now once if you see the three phase average output voltage, anyhow we will derive at the time of explanation. Now VDC, that is nothing but a 3 root 3 Vm by pi into cos of alpha. So this is the expression for single phase as well as the three phase fully controlled rectifier. Now you can notice that here we are getting as a 2 Vm by pi. Let it be cos alpha at alpha is equal to any value. That magnitude is this side is common for both. But here the see 3 root 3 Vm by pi and here 2 Vm by pi. Now here the supply itself has a high Vm is, suppose if it is a 415 volts or 440 volts, something like that. Then what I can write, root 2 into this one will give as a Vm, and then if you want to make it then divided by root 3 also you can use it for phase voltage. So this is the magnitude will be obtained in the case of three phase. That's why first sentence I can see that it provide higher average output voltages. And second one, you can see that output ripple frequency is high. So ripple frequency is high in the sense time duration is small. So the every small interval of time the device is going to be changed over. Now you can see normally in the case of 6 pulse converter or maybe 3 pulse converter, total is one full cycle is a 360 degrees. If you use as a 3 pulse converter by 3, then how many degrees it will conduct? Each device will conduct as a 120 degrees. Now if you go for as a 6 pulse converter, then each pair of the device will conduct as a 60 degrees. So what it represents is every 60 degrees device is going to change over. When compared to the 3 pulse converter, 3 pulse converter device is conducting 120 degrees, here is a 60 degree. That means our intention is in the output side normally as a straight line. So whereas in the DC it has to be straight line, but according to our waveform nature, it will be something pulsating. If these durations are small, then the average, if you take the slope, it will be as a little bit in the straight line in nature. So that is the reason once if you are using as a pulse number is high, obviously will be the benefit, and ripple quantity will be minimized when compared to the single phase. So then because of that, the filtering requirement also will be the less. So when compared to single phase, because it is a very smooth waveform will be obtained. That's why you can use as an inductor. The waveform is passed through the inductor, then you will get it as a output voltage will be a little bit smoother. Filtering requirement, high rating of filters are not required now. So the load current is smoothly, that's what I mentioned. Once the pulse number increases, waveform will be smoother. The load performance is superior as compared to the single phase. So these are the some of the advantages. Now we can see as a three phase half wave control rectifier. Now whereas in the case of single phase half wave rectifier only one pulse, here is a three phase half wave rectifier. So another name for this is a three pulse converter only, midpoint three pulse converter, because when we use it as a transformer, then I call it as a midpoint three pulse converter, or you can see that M3 converter. So that is nothing but a midpoint 3 pulse converter. So here is a 3 pulse converters are dividing as a two things. So one is a midpoint, another one is a bridge rectifier. So these are the, so in the bridge rectifier, we can call it as a semi converter. Semi converter is a bridge rectifier, and then this one we call it as a midpoint. The semi converter also three pulse converter, But full converter, bridge rectifier having two things, no? A semi converter as well as the full converter. So fully controlled rectifier is a 6 pulse converter, whereas in the semi converter is a 3 pulse converter. So these are the one name should be remembered, because based on the output we divided as a controllers. Here you can see if one full cycle of AC supply, if we get the 3 pulses in the output, then I call it as a 3 pulse converter. And suppose if we get 6 pulses in the output, then I call it as a 6 pulse converter. Like that we can divide. But the category also based on the connection orientation, there is a midpoint as well as the bridge. So in the midpoint 3 pulse and bridge 3 pulse, as well as midpoint 6 pulse and bridge 6 pulse. These are the options are available. Midpoint 3 pulse is nothing but this one only, and then bridge 3 pulse is a semi converter. Similarly, midpoint 6 pulse also there, that is a double star converter. So we will see after this. And then this bridge type 6 pulse converter is a fully controlled converter. So these are the some of the broad classification. Now we can see the operation and all. Only very small thing, when the device is going to be forward bias, if you identify, then the remaining part is simple. One thing, when the previous single phase case, at what instant device is going to be forward bias, two things must be required. Or conduction, to conduct any thyristor we require two things. One is it must be as a forward bias. Another one will be it must be firing pulse. Means whenever firing pulse is available only it will start conducting. But forward bias means if anode is positive with respect to cathode, anode is more positive with respect to cathode. So now we can see SCR1 or T1, T2, T3. These are the three SCRs. Each SCR is connected to each phase. One phase, A phase, B phase, C phase, like that. We connected each SCR in the corresponding phase. Now, when SCR1 is going to be forward bias, that is also one thing we must notice. When SCR is going to be forward bias, or SCR1 or SCR2 or 3, when this will be forward bias, one common logic, whenever corresponding phase voltage is more positive, that is a phase voltage is more positive, then that device is the for when comparatively other phases. Suppose A phase device is a T1. When the thyristor T1 will be forward bias, if A phase voltage is more positive than other phases, because when the device want to fire, this A phase means the anode must be more positive than other phases. So that is only the logic we need to remember. At any particular instant, suppose three phase supply is there, any particular instant, see that which phase is more positive than other phases, that phase device is the forward bias condition. That must be logic. So now we'll see at any instant, suppose 0 to 180 degrees instant, at wherever you want to check, or one full cycle, any instant, if somebody asks at this instant which device is going to be forward bias, suppose this is a phase, and similarly other phases also will be there for the three phase supply and all, any particular instant or this instant, in whatever I drawn line, in this instant which device will be forward bias, this is a phase, this is a B phase, this is a C phase. Now at this instant A phase magnitude is this one, and then B phase magnitude is 0, let it be C phase magnitude is a negative. Then which device will be forward bias? Which one is more positive than other, that phase. So A phase is more positive. A phase is connected to T1. So therefore T1 will be forward bias, like that. Or some other instant. You can see this instant. Then in this line B phase is more positive, and then A phase also positive but less positive. and there one is a C phase is a negative. Then which device will be forward bias at this instant? That is a B phase device. Like that, we can easily identify which device is forward bias and whether it is going to conduct or not. How will you know that? If the device is forward bias and at that instant check firing pulse is available or not. If pulse is available, then you can say it is starts conducting. If it is conducting, what is the output voltage? That's all. That is only the 3 points you must remember. When the device is forward bias, then at that instant of time firing pulse is available or not. If available, what is the output voltage? Suppose any instant A phase is more positive, then A phase firing pulse also available, then the thyristor T1 is conducting. If thyristor T1 is conducting, then what is your output voltage? How current will pass? See that it's go A phase, then T1, then it goes to the R load, then it goes to the neutral. Then what is your output voltage? Anybody? Across this load. What is across? When we are doing lab also, no, we are measuring the voltage across the load. So now where the load is connected, that only the point. Now we can see this point, one end is directly connected to the A phase, other end is directly connected to the neutral. Then what is across the load? This magnitude is only the output voltage. So what is this magnitude? A phase voltage. So Vm sine omega t, that is a phase magnitude. So now we can see that sine omega t is your output voltage. Now similarly, if you consider thyristor T2 is conducting, what is your output voltage? Start V, B, it goes to T2, then R load, then it goes to the neutral. Then across the B phase, we can say that it is your output. So what is B phase voltage? Again same as Vm sine omega t. And similarly, if this is conducting, means T3 is conducting, then output voltage is C phase voltage. So like that, it is very common rule whenever thyristor is conducting, in the case of midpoint controller, I am telling, the output voltage is same as the phase voltage, corresponding phase voltage. So A phase or a B phase or a C phase based on the input. If input A phase is more positive, A phase device will conduct, or B phase is more positive, B phase device will conduct if pulse is available. Suppose if pulse is not available, then automatically previous conducting device will continue to conduct up to the natural commutation. So this is the logic behind it. Now we will see the operation. This is the input to three-phase supply. That's why each phase shift is 120 degrees phase shift. This is just simply drawn as a vector diagram. Three-phase supply, A phase, B phase, C phase. Now same thing, you draw the supply. This is the input supply. Now you know the input because we are giving input to the controller. You can see here in this side, this is the input supply. Here we are giving as a something supply in that side. When supply is given, automatically the delta to star connection and primary to secondary, there is a voltage across each phase. And once the voltage is present, now that voltage I drawn here. This is the supply voltage. Once supply voltage is there, now what we have to do is when the thyristor T1 is going to be 5. Now at omega t is equal to 0. You can see here at any point of time omega t is equal to 0. What is the A phase voltage? This is the A phase voltage. Omega t is equal to 0. A phase voltage is VA magnitude is 0. What is the VB magnitude? Negative. VB magnitude is negative. And then what is the VC magnitude? Positive. Now, which device will conduct at that instant of time? Preferably C phase device is a more positive when comparatively A phase. So this is the thing in the previous cycle. So therefore A phase will not conduct at omega t is equal to 0. That is one clarity. And go on. You are increasing the omega t. So 0, then 10 degrees. each line you can see for the later I will show the graph sheets also, just for understanding. This is 0, this crossing is 30 degrees, not a alpha, I am telling omega t, and then this point is 60 degrees, and then you can see that here this point is a 90 degrees, and then this point is a 120 degrees, this is a 150 degrees, this is a 180 degrees. These are the lines just for x-axis splitting. Now once this point is 0, thyristor T1 will not conduct, or A phase device will not conduct. If I go on increasing this, then what will happen? Some point of time at omega t is equal to 30 degrees, this line is 30 degrees, what will happen? A phase device and then C phase device magnitudes, A phase and C phase magnitudes are same. From this point onwards, means exactly 30 degree onwards, omega t is equal to 30 degrees onwards, A phase then C phase magnitudes are same. Then from this point onwards, what will happen? VA will be the more. Once the VA is more, then A phase device is going to be forward bias, not a conduction. Forward bias means it is ready to conduct. At this point of time, you have to check whether pulse is available or not. If pulse is available only, the device is going to conduct. Otherwise, it is only forward bias only. That means we noticed one thing, omega t is equal to 30 degrees onwards, thyristor T1 will be the forward bias. Now that is our reference point. So now we can see that there is this point, I call it as a crossover point or a reference point for the thyristor 1. Similarly for thyristor 2, you can see the B phase. B phase started here. At this point, what will happen? A phase is more positive and then C phase is a negative and B phase is a 0. Therefore, B phase device will not forward bias because A phase is more positive. That means A phase device will be forward bias. But after this, again from this point to 30 degrees, then what we noticed is A phase and B phase magnitudes are same. From this point onwards, A phase is going to be forward bias. That is the reason we can say that, B phase is going to be forward bias. So this is the crossover or reference point for the thyristor T2. That this is for thyristor T2 and this is for thyristor T1. Similarly for C phase, this is for thyristor T3. Now we identify the crossover points. What is the crossover point? Omega t is equal to 30 degrees is nothing but a alpha is equal to 0 degrees. That is the first statement from this. So whenever you want to represent in terms of alpha, you cannot measure from 0 onwards. You have to measure from crossover onwards, because from that point is a reference point for the particular thyristor. So this is the crossover point for T1, crossover point for T3, T2, T3. So these are the, and cycle is going to be repeated. This is for T1. And like that, we identify the crossover point. So whenever you want to put the firing pulses, from that point onwards, we have to put the pulse. This is for T1 and then T2, then T3. You want to can make it 2, 3. 1, 2, 3 pulses. Now what we have to do? We have to provide the firing pulses. Once if we provide the firing pulse, then only we have to draw the output voltage waveform. Now we can see that how this is your output voltage waveform for alpha is equal to 0 degrees. Where I have to put the firing pulse? So because you can see here, I am providing the firing pulse for T1 at alpha is equal to 0. How will you provide the firing pulse? You can say up to pi also you can give firing pulses. This is for alpha is equal to 0 instant. Why I started this point? Because this is a reference point. This is the reference point for T1, reference point for T2 and T3 and so on. Cycle is going to be repeated. 1, 2, then 3. This is the, again this is a 1. So alpha is equal to 0. That will be the firing pulse. Similarly for T2, where this is for T1. and where I have to give the firing pulse to the T2 for this reference point onwards, because that is the reference alpha is equal to 0 instant. Now we can start firing pulse here, and if you want to make it up to end also you can give it, or just spike pulse also you can give. And then what is third pulse? I have to give the starting point is here for the thyristor T3, and you can give it as a, this is the firing pulse for IG1, IG2 and IG3. Once firing pulse is available, and you have to draw the output voltage waveform. How will you draw the voltage waveform now? At this point, up to this, no device will conduct, let it be. We started here and pulse is available. T1 will start conducting. If T1 is conducting, what is your output? Same as the input. This is your output. Whatever I am shading red, that will be as the output. Once this point reaches, what will happen? Even though firing pulse is available for thyristor 1, but what will happen, this crossover point onwards, A phase magnitude is reducing and B phase magnitude is increasing. That's why A phase will be the reverse bias and B phase will be the forward bias. So now the device will conduct from this point onwards T2. If T2 is conducting, your output is same as the B phase voltage. You just shade the B phase. Now this crossover reaches, B phase magnitude is decreasing, but C phase magnitude is increasing. Then the device B phase will be turned off and then C phase will start conducting. Once C phase is conducting, your output is same as the input. So this is the outbound cycle is going to be repeated. So now one full cycle of AC supply, we got three pulses. This is one pulse, second pulse, third pulse. Then output, you are getting three pulses in the output. Then this is a three pulse converter. So now you can draw output waveform separately if you want. This is the output voltage waveform for alpha is equal to 0 degrees. Now the question is, suppose I want to draw the waveform for alpha is equal to something 10 degrees. Then what I have to do? What is the requirement here? Once if I change the alpha value, instead of 0 to 10 degrees, what I have to do? Starting point will be differ. What is starting point? We have to start with counting always from crossover, whatever may be alpha. It is this crossover, I call it as a alpha is equal to 0. All the crossovers I mention alpha is equal to 0. And now I want to measure the alpha value from this point onwards. You can count alpha from 0 onwards. This is the way you can just count each. I told no, this is 30 degrees, then the 60, 90, 120 or like that. Now I want to keep alpha is equal to something 10 degrees. This is the 0 points. From this point onwards, I have to count the 10 degrees. How will you count 10? This is 0. And now you just count like this. This may be 10 degrees. Now correspondingly, you can make it as a 10 degrees line. So here you can draw line 10 degrees. So just here I measured 10 degrees like this, and similarly 10 degrees like this, and here like this, and cycle is going to be repeated. Now you have to put the firing pulses here only. This is for T1, then this is for T2, and this is for T3. You want, you can make it full or maybe spike pulse like this, and cycle is going to be repeated. This is for T1. So 1, 2, 3. Now how to draw the output voltage waveform? How will you draw the voltage waveform? You can see there is a one, you can notice one thing. Here I started, no? From this onwards only A phase will conducting. How long? Now we can notice this A phase is the more positive and firing pulse also available. It is conducting up to here. From this onwards, whether B phase device will conduct or not, you can see B phase device is the positive only, but firing pulse is not there at this crossover point onward, because we mentioned the firing pulse at the alpha is equal to 10 degrees. No, that's the reason this A phase will continue to conduct until we can see that next firing pulse is available. Then what will happen? A phase will continue to conduct, then it is move on to B phase because pulse is available after 10 degrees. So then it goes to B phase. Again crossover reaches, you can check it, pulse is not available. Pulse is available only after 10 degrees. So this is the firing pulse after 10 degrees. That's why A phase will continue to conduct, then it move on to let it be as a C phase. Then C phase will continue to conduct, then move on to A phase. Like this, your output voltage will be like this. Then what is the difference previous one and this one? We can notice the waveform. Earlier, if alpha is equal to you can see alpha is equal to 0 degrees, what we are getting, something we started like this. This is a 3 pulses. Now we start 10 degrees, it will continue to conduct. Then this is the output voltage waveform, alpha is equal to 10 degrees. Like that, if we keep on increasing alpha value, what is the difference is, instead of starting this point, we started here, later we'll maybe started here. So like that, every instant of time you can able to put the firing pulses. Now this is the alpha is equal to 30 degrees. Alpha is equal to 30 degrees means that omega t is equal to 30 plus 30, because I mentioned omega t is equal to 30 degrees, alpha is equal to 0 degrees. If alpha is equal to 30, I want to put it, then the count with respect to omega t must be as a 60 degrees. Like that, you can see the waveform itself. This is the 0 and this is 30 degrees, then this is the 60 degrees, instant. And then at this point you have to put for alpha is equal to 30 degrees. Suppose if alpha is 60 degrees, you have to put the firing pulse here. If alpha is equal to 90 degrees, you can put the firing pulse here. Like that, you can count the alpha from the crossover onwards. This is only the logic for throughout the three-phase control rectifier. You have to identify the crossover. Wherever the corresponding phase is more positive, this is the points is the crossover or measuring point or a reference point. This point I call it as alpha is equal to 0. So after that, whatever alpha you want to put it, from this onwards you measure the x-axis degrees, and wherever you want to put, you can put the firing pulses. Now we'll see waveforms for different values of alpha. Now this is alpha is equal to 0 because we started putting firing pulse at alpha is equal to 0, because this is a crossover. We mention as a firing pulse, one is here, another one is here, third one is here. So then we got the output voltage like this. Now if alpha increases, suppose alpha is equal to something 20 degrees, let assume that alpha is our alpha is 20 degrees. Then what will happen? Alpha is 20 degree. Where I have to put the pulse? Here is the firing pulse, and here is another firing pulse. Here is the third firing pulse. Now you can see, you just project like this. What will happen? We counted from 0 onwards 20 degrees, something like this, and every instant count always from the reference point onwards. So this is a 20 degrees line. If you extend that, you can put the firing pulse for alpha is equal to 20 degrees, and here you can get the firing pulse for alpha is 20 degree, and this is for alpha is 20. So like that, we provided the firing pulse. Now once pulse is there, it is more positive, so therefore T1 will start conducting. If T1 is conducting, current is passing like this, the A phase is your output voltage waveform. If A phase is output voltage waveform, then what is your output? You can draw same phase from the starting point onwards. Now you can see this is our starting point. You just shade the A phase up to crossover. You check it whether pulse is available here. No pulse. Pulse is available only here. That's why what you have to do, this will continue to conduct in the A phase only. Then pulse is available, it will move to B phase. Then pulse is available, it move to C phase. So like this, it is going to be your output voltage waveform. So like this. And now you further increase the alpha value, suppose 30 degrees. What will happen now? You can see voltage waveform beyond 30. Exactly 30 means it will get, I will shade exactly 30 degrees also. We will start here. This is the axis. Another color. See, this is the 30 degrees per impulse, and we will shade like this, and then it reaches this point. Again, per impulse is available. This is exactly 30 degrees. What will happen? This is naturally 0, and again next firing pulse is available, B phase will conduct, next firing pulse available, then C phase will conduct, again cycle is repeating, A phase and so on. Now exactly 30 degrees, this line is getting as a natural 0 point. Now if I increase alpha beyond 30 degrees, suppose I will mention as a 60 degrees. How to count 60 degrees? This is 0, then 30, then 60 degrees. 60 degrees is nothing but alpha is equal to 60 degrees is nothing but omega t is equal to 90 degrees. In the x-axis omega t, that peak, whatever the magnitude peak is there, that is alpha is equal to 60 degrees, or omega t is equal to 90 degrees. Now we have to draw the output voltage waveform. How will you draw that? We started here, and it will continue to conduct, and it will get this point. Now I will provide all the pulses first. For alpha is equal to 60 degrees. See, this is the line, alpha is equal to 60 degree. How you got this line? From the crossover, you measure the 60 degrees. So this is the crossover 0, 30, 60. So 2 centimeters, or you can say the each line is 30 degrees. Let's consider in the graph sheet also. Yeah, 2 centimeters is nothing but 60 degrees. Now this is for T1, then T2, then T3, then T1. So this is the case. Now you have the pulse at this points. We have to draw the output. These are the pulses. Let us assume that. How to draw the output? You start with this point, because we'll take just a minute. I started this, which is the device will conduct, because this is A phase is more positive, pulse is available, this is a pulse, and A phase is more positive, or output is A phase only. Crossover reached, we can see no firing pulse is available for B, so A only continue to conduct. It reaches to natural pi, and check this point, here no pulse is available, but the supply reaches to the natural pi. That is a phase, no? A phase R load. Then what will happen? This supply is natural 0, then automatically thyristor T1 will be turn off. It will be open. Then no pulse is available for B, then what it will do? It will be turn off. So it will be 0 remains. Then once the again alpha is equal to 60 degree reaches, then what will happen? B phase is more positive. Here also B phase is more positive, because no firing pulse is available, that will be 0. And again B phase is output, and here no pulse for C, it will continue to B only, and reaches to natural pi, and still no firing pulse is available. That's why B phase device will be open, then the output voltage will be 0. And again C phase will start here, then the output will be like this, 0 natural 0 will remains 0, then again cycle is repeating. So this is the output voltage waveform for alpha is equal to greater than 30 degree. One thing we noticed in our waveforms earlier, whatever we drawn, you can see that alpha is equal to 0, we got like this, and alpha is equal to 10 degrees, something we got like this, not be that much down, and then alpha is equal to 30 degrees, will get like this. And beyond 30 degrees, if we keep alpha is 60 degrees, the turn off point will be the same, but remains in the 0, and it will be like this. This is the alpha is equal to 0, This one is suppose some 15 degrees, this is 30 degrees, this is a 60 degrees. If you keep on increasing alpha, then what will happen? Starting will vary, ending will be common because natural pi, and then discontinuity term will be more, and then we get output will be like this. Then what is observation? By increasing the alpha up to 30 degrees, we are getting as a continuous. Exactly 30 is a natural 0, and beyond 30 degree it goes as a discontinuous because it remains in the 0 instance. So that is the two modes of operation here. One is a continuous mode, another one is a discontinuous mode. So continuous and discontinuous mode of operation. Continuous firing angle alpha is less than or equal to 30 degrees, and alpha greater than 30 degree, we call it as a discontinuous mode of operation. So this one is a continuous mode, another one is a discontinuous mode of operation. So these are the two things. Now we can see, that's what I mentioned. Continuous mode means by seeing this waveform up to 30 degrees already drawn. I will show once again the individual alpha waveforms also, because in exam they may ask particular alpha. It will not be generalized equation waveform. Draw the output voltage waveform for alpha is equal to 45 degrees, or alpha is equal to 60 degrees, or alpha is 75 degrees. Correspondingly, we have to draw. By seeing here, I mentioned this is 0 reference for all the thyristors. From here onwards, we can count alpha value. Suppose alpha is 75. Where I have to put the pulse? From this point onwards, count the 75 degrees. And then we have to draw the firing pulse. From here onwards, count the 75 degrees, and then you can draw the firing pulse. Or omega t is equal to 30 plus 75. That point also you can put, both are same. If you count here directly alpha, if you count from 0 onwards, you have to add 30. Then will become as a alpha. That's all. So either of one, but preferably use the crossover. From this onwards, you count the alpha, direct alpha, you will get it. For all the cases, crossover point onwards, respect to thyristor firing pulse, you can count and put it there. Now, this continuous means greater than 30 degrees. I will show waveform. This is whatever I shade the color, that will be as a output voltage waveform. Other than that, as normal input, and we will get the output voltage waveform like this. This is alpha is 0, and alpha is 15 degrees. What will happen? Instead of starting, you can see here something like this. Instead of starting this point, we'll start here. What is that? This gap is a 15 degrees. Earlier this is 0 and this is 15. Again this is 0, this is 15, like this. And every instant we can able to put alpha value here, here and here. So that is the alpha, and again the same phase will continue to conduct, but this crossover we won't be transferred to B phase, because B phase pulse is available only here. That's why A phase will continue to conduct, then it will transfer. Again C phase, it will transfer like this. Is alpha is equal to 15. Now alpha is equal to 30 degrees. Exactly natural pi will get it starting this point, and we'll get it this point and so on. Exactly 30 is a natural pi. It is the end of the continuous mode of operation. Now if I increase beyond 30, what will happen? If I increase the alpha beyond 30 degrees, natural pi will be remains. Now once the voltage is 0, because of the resistive load, current also will be 0 here. If current is 0, automatically what will happen? Thyristor is going to be open. So if thyristor is open, then what you can do? Only the thing is thyristor will be open. So current is 0, thyristor will be open. Now if you want to draw the current waveform of any one for resistive load, same as this is the current waveform. Magnitude will reduce, and here, and again here something I reduce the magnitude. So that green lines are the current, and here also up to this point you can get it, and here as such, but just make it like this. This is the current waveform for alpha is equal to 0, and then for alpha is equal to something like this. This is a 15 degree. So the green lines are the current waveform. Now once you can see the current is 0, automatically thyristor is open. If thyristor T1 is open, but T2 will be fire only at this point, that's why this duration remains in the 0. That is the reason we will get it as a discontinuous mode of operation. Now we'll see the derivation part, continuous as well as the discontinuous. How will you derive the any waveform? I mentioned you one full cycle you can take it and integrate it. That is only the derivation part. This is the waveform for alpha is 0 or 30 or 15 degrees, anything. What is the starting point? What is the ending point? You identify and integrate it. You will get it as a average output. So now what I want, average output voltage waveform. You can see here. This is the VD, anything VDC I want. How many pulse one full cycle I got? This is one pulse, second pulse, three pulse. So whereas in the single phase case, two pulse what I wrote 2 by 2 pi. Now it is a 3 pulse. I am integrating only one pulse and multiply by 3. That will give as a 3 pulse output. And if I'm 2 pulse means I integrated 1 pulse multiplied by 2 will get 2 pulse output, like that. So now this is a 3 pulses I have, 3 by 2 pi, then integral. What is this starting point? You identify. What is the ending point? You identify. And then how many degrees each device is conducting? What is this duration? You can see. Blindly you can measure, total is 360 degrees now by 3 pulses, then that will give as a 120 degrees. So if I identify starting and plus 120 degrees, you will get it as a this point and integrate. What is output? A phase. What is A phase? Vm sin omega t d omega t. And limits. What is starting point limit with respect to d omega t? No. What is starting point? This point is 30 degrees and for alpha is equal to 0. So in general, what is this point? This is 30 omega t and plus this alpha. So this is the starting point. And I will get the starting point omega t. I want starting point with respect to omega t. So every case, this is the reference from alpha. Ending point, I mean this point will be obtained 30 plus alpha. So therefore you can make it this is the first lower limit. You can valid for all the cases. Any alpha you can put, starting point is always 30 plus alpha. Reason is this is crossover 30 plus alpha. Then if you add 30 plus alpha, you will get starting point of here, starting point here, or all the cases will be the starting point. Therefore 30 plus alpha. What is ending point? Duration. All the cases duration up to continuous case I am deriving, and all the cases duration is a 360 by 3, then 120 degrees. So starting alpha plus 30 starting plus 120 degrees, that will be the ending point. Over. Our integration is over. Simply V out or VDC, that is equal to 3 by 2 pi integral alpha plus 30 to alpha plus 30 plus 120. So 150. Output is Vm sin omega t d omega t. Over. Integrate this, you will get it as a average output voltage of a continuous mode. Now, how will you get the discontinuous mode of operation? So, starting point is common, continuous or discontinuous. What is the difference of discontinuous mode? Ending point. This is the ending point. Here, the ending point is fixed. Okay, whereas here the ending point is 120 degrees, all the cases we added starting plus 120. But whereas here it will not be 120. You can count if you want. Starting plus this ending is fixed, natural pi. Once this waveform reaches this point, whatever alpha if you put, automatically I draw no for 90 also you can see it will be the ending point. Now this starting and then ending. So if you further increases, your output voltage waveform will be like this. That means ending will be fixed. It won't be as a 120 degrees because only small duration it will conduct. Up to pi only it will conduct because of the resistive load. So then what is your output voltage? VDC, that is equal to 3 by 2 pi starting alpha plus 30, ending is pi Vm sin omega t. That's all. So that is only your ending point. So like that you can integrate, you will get it as a, this I call it as a discontinuous mode of operation. Earlier expression, whatever I drawn 3 by 2 pi alpha plus 30 to alpha plus 150, that is Vm sin omega t, that is for continuous mode of operation. This one is a discontinuous mode of operation. So now I derived here, you can see same 3 by 2 pi alpha plus 30 to alpha plus 30 plus 120, that is equal to, in output is Vm sin omega t. Integrate that, what I got is 3 root 3 Vm by 2 pi into cos alpha. This expression is valid only alpha 0 to 30 degrees. This is very important. Alpha range is less than or equal to 30 degrees. Up to that only we have to use this formula. Suppose in exam they ask the average output voltage of a controller for alpha is equal to 45 degrees. Then what you have to do? You cannot substitute alpha 45 in this equation, because alpha 45 is a discontinuous mode of operation. In that expression we have to use it, but whereas here it will be as a alpha is 30 means you can use this expression, or 20 means you can use this, but beyond 31 degree also alpha value you cannot use this expression. That will be coming like this. So you can see after continuous I will show that discontinuous. Maximum output how will you get? Any expression, maximum output will be obtained by putting alpha is equal to 0 degrees. That will be as a maximum output voltage waveform. Average output current, once if you know the voltage divided by R will give as a current. And conduction of a thyristor, as I mentioned you, there is a each device total is 360 by 3, each device is going to be conduct 120 degrees. That's why I mentioned conduction of device is 120 degrees. In that average, how will you get the average? Once you know the total output is I naught, total is 360 degrees, it is conducting only 120 degrees. Then what is average? I naught by 3 is average. RMS also you can find it. I naught into same thing root, that will give as a RMS, I naught by root 3. Similarly, we will go for as a discontinuous mode of operation. What is the difference of continuous and discontinuous? Only the limits is going to change. Here the limits are alpha plus 30 to ending point. No, that ending point is fixed there. That will be as a pi. So that we can make it as a pi. So that is your ending point. So now you can get it as a your conduction angle of a thyristor for discontinuous. What will happen? Ending is pi, I told, no? That's the reason from that point you can get it as a starting is 30 plus alpha to how long it will conduct? Up to pi only. Whereas earlier it will conduct up to 120 degrees, means alpha plus 30 plus 120 is your final ending point. But now for discontinuous mode, this will start with alpha plus 30, ending will be pi. Then what is difference? Pi means 180 and minus 30 minus alpha. That is your conduction period. So 180 minus 30 is a 150 minus alpha is your conduction period for discontinuous. So it won't be as up to 120 degrees, because alpha is beyond 30, no? So if you keep for 50 degrees, then conduction is only 100 degrees. When compared to the continuous mode, continuous must and should it will conduct 120 degree, you will get more output. But discontinuous mode will get less than 120 degrees. That is as simple. Now you can see the derivation part as usual, 3 by 2 pi alpha plus 30, but ending is pi. Output is Vm sin omega t. You just integrate, you will get the expression of this. So what is this expression? For discontinuous mode of operation. Now if the question is asked to explain or find the average output voltage for alpha is equal to 45, you can substitute the formula is this formula. You cannot use previous formula. Previous formula is only up to 30 degrees only, you can use that formula. Now remaining RMS, all these things as usual, square it whole power 1 by 2. To do that, we'll get this is the VRMS. For alpha is equal to greater than 30 degrees. That is a discontinuous mode of operation. Average output current, output voltage divided by R will give as a current. It is a VDC. Either any one notation you can follow. Either it is a VDC we used upper side, so you can use this also VDC. VDC by R, that will give as a average output current. Here also current IDC, if you want you can use IDC. Like this. The remaining quantities also IRMS, VRMS by R, and average thyristor current I0 by 3, and RMS thyristor current IRMS by root 3, and efficiency output by input. Output is PDC, input is PAC. So that is we can get it. And volt amperes, it is a 3-phase supply, 3 VS IS, and transformer utilization factor, that is a PDC by volt amperes. All as usual formulas, only the expressions will change in the case of what you call it as VRMS and VDC. These two things will modify. Other than that, everything is same. And output power I square R, or V square by R, whatever formula you want, you can use it. VDC, VRMS into IRMS, that is also power, and power factors. Now, if it is a RL load, what will happen? Only thing is, you just remember here the waveforms. As you are aware that in the case of single phase, what we call it as single phase control rectifier, what is the difference between R load and RL load? Whenever conduction is going to be turned off at pi, but because of the inductor, this will continue to conduct. You can see that up to continuous is as usual, it won't be happen anything. And discontinuous mode operation case, if it is RL load, it will come like this over. Because of the inductor, it is having something inductance value, that plus and minus will charge. Later it will become minus and plus. That plus it will continue to conduct in the A phase only some more time. And similarly for B phase. So wherever 0 will be there, you will get it as a negative. So means same device is going to continue to conduct. Earlier, why it is stopped? A phase device is stopped at this point, no, at natural pi, because current also 0. But now what will happen? There is an energy stored in inductor. That energy is going to be dissipated in the same device. That's why it is A phase will continue to conduct until next firing pulse is having. Now B phase, then C phase. Now your voltage waveform will be like this. That's all. Exactly. So now RL load case also up to 30 degrees, same waveforms. Now here no more continuous and discontinuous, everything is continuous only. This is the continuous mode of operation, whether alpha is 0, and RL load case also alpha is 0 means same waveform, alpha is 15 degrees same waveform, 30 degree also same waveform. Only beyond 30 degrees, you can see that beyond 30 degrees normally you will get it as a what we call it as 0 here in the case of resistive load. So after 30 degree, in the case of resistive load, you will get it as a turn off. So that is the point. Now because of inductor, this will not be turn off, that current will continue to conduct. So then we move on to A phase will continue to conduct until next thyristor is going to fire, and B phase will continue to conduct until next thyristor is going to fire. Like this, that is only the output voltage waveform. After 30 degrees, wherever 0 is there, you make it as a negative, that become as a RL load. Suppose you try to find, if I connect as a freewheeling diode across load, this is a freewheeling diode across load. What is the modification of the waveform? You no need to mark up any waveform. Once if you know one set, the remaining only modification point. R load and RL load modification, wherever 0 is there, you will get it as a negative voltage 0 portion. Same previous phase device will conduct. Now, if it is a what I call it as with freewheeling diode, again it will become same as this. It won't be negative. It will be turn off, because current will be present like this with freewheeling diode. Here this portion will carry by the freewheeling diode, this portion carry by the thyristor. Then the voltage waveform same as the R load only, but current waveform carry by the freewheeling diode. So that is only the difference, R load, RL with freewheeling diode. Now we'll show that also. For inductive load, explanation point, one statement. You can see that the L is there here. Because of that, up to 30 degrees as usual. That's why it won't be change anything. Wherever firing pulse, this is a reference again, same crossovers are reference, and count the alpha 30 degrees or 60 degrees, whatever you want to put. From the crossover you can count the alpha. So now you put the firing pulses, then the corresponding phase device is going to conduct. So now up to what you call it as this portion is same, so it won't be happen anything. Now beyond 30 degrees if I keep, what will happen? I mentioned alpha is equal to 60 degrees. Earlier waveform for alpha is equal to 60, you can see the waveform will be started here only. Starting won't change anything. Ending here natural pi will occur. That's why I made it 0 like this for R load. Because supply is 0 and voltage is 0, current is 0, device will be turned off directly. But now the inductor will store energy. That energy is going to be dissipated in the same phase, A phase only. That's why A phase will continue to conduct some more time. If A phase is continue to conduct, what is the A phase magnitude? That magnitude is nothing but a, from this point onwards is a negative. That's why we draw on the negative. That's all. Then again B phase will conduct. Again it will continue. So that is the difference of R load and RL load. Only thing is it won't be stop at natural pi. It will continue to conduct up to next device is conducting. Suppose inductor value is small, then what we can do? We continue to conduct only, but not up to the next thyristor conduction. So what we will do? We will continue to conduct only some duration. Then this point from here to here 0. Then thyristor. So that is the, you can see I will draw here. It will conduct. This is the x-axis and will come and 0 if it is a discontinuous. Suppose I am telling, because inductor is small, otherwise everything is continuous. If large inductor is there, it will continue to conduct like this. Here also continue to conduct up to 5 plus alpha, otherwise it is a beta. That is the common for all the cases. Now again you change the alpha value 60 by something else, then what will happen? Positive duration, negative durations are equal, average will get it as a 0. Same thing, starting only changing and ending what? Up to next device is going to fire. So that is the simple logic. We started alpha 30, we'll get like this. Beyond 30 it is coming same phase will continue to conduct, and then 90 degrees we started omega t is equal to 90 plus 30, 120. You can see that x-axis 120 we started, and this A phase it changeover will not be happened, only pulse is available up to this point, and it come to here, it won't be natural 0 because inductor is there, the same phase will continue to conduct, then the same phase will get the output, and then pulse is available for B phase, it will transfer like this. This is the output voltage waveform for RL load case. And similarly you can see that I given different alphas supply. In exam you have to draw whatever alpha they asked, only that sufficient. Here I given all the different alphas for understanding. This is the Vs and alpha is 0, means all the 3 pulses will get it. A and B and Cn is output now each phase, and then alpha is equal to 30 degrees, exactly it reaches to the natural 0. Then beyond 30 degrees for RL load it will come negative. That is only the difference. With freewheeling, suppose if I add with freewheeling same waveforms, this is same, this one is same, third one also same, only here it will make it 0. That is for with freewheel. RL only with freewheeling we make it 0. So here also we'll make it 0. So that is the case. And then derivation part. Derivation is common, no? Alpha plus, because it is a continuous, I said alpha plus 30 plus ending point is alpha plus 30 plus 120. So that will become as a same expressions, and you simplify 3 root 3 Vm by 2 pi into cos alpha. This is common, so you don't have for discontinuous. Let consider inductor is large, and then we'll get it as this is, this expression is valid for 0 to 180 degrees of alpha. But whereas in the case of R load case, one expression, first expression is valid for alpha to 30 degrees, means up to 30 degrees, and then second expression is valid for alpha greater than 30 degree. But now in the case of R load expression only this one, this is the first expression. Now for the RL load, this expression is valid for all the alphas. Based on the load, you have to substitute the formula. That only different. And RMS, everything is same. Once voltage is same. Now with freewheeling, I add the freewheeling. Your waveform is exactly same as R load waveform. It won't happen any change because wherever the negative is happened in the RL load, that will be suppressed to 0. Then this waveforms is exactly same as the R load. That's all. So we'll see the next class. This is three pulse. You can observe our waveforms whatever we mentioned. This is for three pulse midpoint converter. This one whatever I explained today, this is a three pulse midpoint converter. Next we'll see that six pulse midpoint, then we'll go for as a bridge. So bridge we have three pulse bridge, six pulse bridge, that only the left out, and finally we have as a dual converter. So that is the topics need to cover today. Three pulse mid is over, then six pulse mid I will explain one question, then bridge type three pulse and six pulse, then final one is a dual converter. So that is all our syllabus of this unit. If you have any doubt, you can ask me. Otherwise, you can leave.